Katrina here, and today we're going to talk all about expected value and variance of random variables. Be sure to watch to the end so that you get all the examples for both continuous and discrete random variables, and please subscribe for more videos. Okay, let's dive in with looking at discrete random variables. Recall from my earlier video that discrete random variables are countable, or they're either countably infinite. So they are not continuous, they are not infinite. They take on discrete, countable, or infinitely countable values. So let's start looking at what expected value is and its relationship with discrete random variables. So in particular, if x is a discrete random variable with all possible values, x1, x2, all the way to xi, and a PMF, which is a probability mass function, p of x, then the expected value, which is also known as the mean of x, is written in the following way. So the expected value is written as e of x, so the expected value of a random variable x, and it is given as the sum over all values of I of xi multiplied by p of xi. So we're taking that specific value, xi, and we're multiplying it with the value of the probability mass function at that specific point. Just so you know, there's other ways or other notations that people commonly use. For example, you might see this written as mu, like this, sub x, or even just mu. And this is like a general notation that people will use often to represent the mean of a random variable. The other way we can think of this is as a weighted average. So that's kind of a maybe more intuitive way that a lot of people might see this, because you're taking the value times the multiplied by the probability of that particular value occurring. So why don't we take a look at an example to help us get a better understanding of what this is. In my previous video, I talked about heads, tails, coin toss, and in this coin, we have a fair coin. So the fair coin has two possible outcomes. It can either be heads or it can be tails. And in particular, we have some subset S. So we've tossed the coin twice in a row, and we want to see what is our outcome. So in our sample space, we have the list of all our outcomes. So on the first toss, we have two heads. On the second toss, we get heads then tails. Our third one, we get tails then heads. And on our fourth one, we get two tails. And we want to state that our random variable x is the number of heads that we get. So that is how we are quantifying this random variable. This is how we're mapping this almost kind of generic or conceptual idea of coin tosses, and how we are taking it and mapping it into the real line, because number of heads is a discrete value and it's a real number. Okay, so by doing this, we can go ahead and calculate the expected value. So right away, we know that when we have two heads, for example, we have that our random variable here is 2 because we're counting the number of heads. Here x is 1, here x is also 1, and when we have two t's, our x equals to 0. So these are our kind of individual events, or these are our possible values. So we can think of this as our x1, x2, x3, and x4. So now let's go ahead and calculate the expected value for this problem. So recall our definition from up here. We take the sum of our value multiplied by the probability of occurring. So let's go ahead and do that. So our expected value equals to we'll start with our tails first, so our t. So we have our x is 0 multiplied by p of 0, and then we're going to add this one next. We have 1 multiplied by p of 1, and then plus we have 2 of p of 2. There we go. So we have 1, 2, 3. We have all the values right over there. So now let's go ahead and fill out what our probabilities are. So this equals to 0 times 0.25 plus 1 times 0.5 plus 2 times 0.25. So all these values we can have found from a table of values, or we could have calculated that manually, but for the sake of this problem, let's just say that the P0, P1, and P2 values were all given to us, and then this is how we would go ahead and write them out. Okay, so now if we simplify this, we can see that we get 0.5 plus 0.5, which equals to 1, because we see that this term gets canceled out, and we can then calculate the rest of that over there. So there we go. So that means that our expected value is 1. So that means we expect that the number of heads obtained in 2 tosses of a fair coin will be 1 on the long run, or on the average. So this is kind of, like we said, it's the on average, or we can think of it as in the long run. So if we were to repeat this experiment many times, this is the outcome that we expect to get the most often. So in the long run, or on average. Okay, so that covered our PMF, our probability mass function, and the expected value of a discrete random variable. The next thing we're going to do is we're going to look at how to calculate the variance of a discrete random variable, so we can go into other definitions such as the standard deviation. So let's dive into that definition next. So we have the variance. So definition. We want variance of our random variable x. And again, we're saying that x is discrete. So this is given by sigma squared, which can also be written as var x, and this equals the expected value of the difference between our random variable minus its average, all squared. And our standard deviation, this is another important statistic that we should all know. So our standard deviation tells us how much our data is varying or differing from our mean. So this simply just equals to the square root of the variance. So we write this as sigma equals to the square root of the variance of x. Okay, so we can see that direct relationship between our variance and our standard deviation. However, I want to show you another way for how we can represent the variance. So this way here might be a little bit difficult to calculate directly. If we look at it intuitively, it makes sense. We're looking at each random variable x and what is its difference with respect to the mean that was calculated. And then we are squaring that and taking the expected value. However, we can have an alternative definition to variance. So we can also have that variance of x equals to e of x squared, so the expected value of x squared minus our mu squared. So this also equals to the expected value of x squared minus the expected value of x all squared. So just please be careful. make a little arrow here, that e to the x squared on the inside does not equal to e to the x squared on the outside. These are two separate definitions, okay? So for this one over here, we find the expected value and then we square it. But for this definition here, we actually have to change our fundamental definition for expected value. So instead of taking the sum of x multiplied by our p of x, we instead then have to take x squared multiplied by p of x. So again, this is just another way to represent our variance, and this is often used a little bit more and is a little bit easier when we're trying to calculate that. So again, now you have the definition, how to find this guy over here. You just take the same definition as before, but you just square that additional x value while you're doing the sum for each term. Okay, so that is our variance and our standard deviation. So the next thing we're going to move on to is looking at continuous random variables, and we're going to see how their definition is different from that of a discrete random variable. So let's move on over there right away. So let's dive in. If x is a continuous random variable now, and it now has a PDF, a probability density function denoted as f of x, then the expected value, or the mean, is given by this formula. So again, we can write the mean as our mu, we can write it as mu sub x, and we can also write it as e of x. So if you recall, when we have continuous variables, that means that there's an infinite amount of values that it can take on. So instead of doing a sum, we have to integrate to find our results. So this is the integral from negative infinity to infinity, and then we have x multiplied by f of x, and we're differentiating with respect to x. So you can see that this middle part here is very similar to how we did our calculation for discrete variables, but now we are integrating instead of taking the sum. So we can also now move on to find the variance. Okay, so we already know previously from our discrete situation, when we have discrete random variables, that variance of x equals to e to the x squared minus mu squared. So that fundamental definition is the same. But what's different is how we actually calculate our e of x, right? Because we have to use this new integral notation. So this here just equals to the integral from negative infinity to infinity of x squared multiplied by f of x dx. So that is this value over here. Remember, because we have to square this value. So that represents that term. This term is this term. And now let's do our negative mu squared. So that is just simply this one over here. So we do minus the integral from negative infinity to infinity of x times f of x dx, and then remember we're squaring on the outside. So that is our integral definition there of the variance, and same as before, our standard deviation of x is just our root of our variance of x. Okay, so these are really good kind of notations to have down. So before we dive into an example, I just wanted to show you a few other important properties of our expected value. So expected value also has a linear property if we're dealing with linear functions. So what I mean by that is if we have some g, which is a linear function, so we should all be familiar with linear functions by now, And then, so that means that we can write g of x as some, let's say, ax plus b, our typical notation where a is our slope and b is our y-intercept. Then, for our expected value, if we take the expected value of g of x, then we can actually separate it linearly. So let's derive that. So that means we have the expected value. We're going to sub in our g of x into our brackets here. So we've got ax, remember x is our random variable, plus b. And now this equals to, we can take this coefficient of x out. So we'll take it one step further. So let's divide this into two. So we can look at both of these terms separately. So that means we can take e to the ax plus e to the b, where b is a constant. What we can do now is any coefficient of x can be taken out of the brackets and just become a coefficient of the expected value. So that means you have a multiplied by e of x. And then now what do we do here? We have the expected value of a constant. Well, what's the average of a constant? It's simply just the constant itself. So it would simply just be plus b. So that's really neat how this case is referred to as the linearity of expected values. So that's really neat how we can just take things out just like that. So essentially what that means is we'll just look at the rules. The two main rules that we did here is the expected value of some constant equals the constant. And if we were to have a coefficient in front of our function, c g of x, we can simply take the constant out and then just have our expected value of g of x. So that's awesome. So now that really helps you understand expected value and variance, and it allows you to do some manipulations there. So let's close off by looking at an example of trying to find the expected value when we have a continuous random variable. So we know what our formulas are. So now, for example, we will have our function equals to some piecewise continuous function. So if you see in my previous video where I talk about probability density functions, one of the criteria is that it has to be piecewise continuous. So say we have this function over here. So we can tell that it's piecewise because it takes on a different function for different values of x. So this function equals x when x is between 0 and 1. It's equals to 2 minus x when x is between 1 and 2. So greater than 1, less than or equal to 2, and then 0 otherwise. Okay, so let's go ahead and calculate the expected value. So we know that the expected value equals to the integral negative infinity to infinity of our, we can go up and check our definition, x multiplied by f of x. So we have x times our f of x dx. Okay, but what about our integration bounds? In our general example here, we have negative infinity and infinity. However, for our specific PDF that we're looking at, we see that we have bounds on our x. So that means that we can use those bounds as our integration bounds, and we actually have to separate this integral because we have these specific bounds. That means that there's going to be points along this function that are non-integrable or non-differentiable, so that's why we have to separate out this integral. So this equals to, let's separate this out. We'll start from our smallest one. So we're going to go from 0 to 1. Our function is just x. So we have x times x dx. Plus our next bound. We go from 1 to 2. This one over here. So now our function is 2 minus x. So by definition, we do our x multiplied by 2 minus x dx. And let's see what our last one is. Well, it's 0 otherwise. So that means we would just have some function where we take the integral and we have x times 0 d of x from 2 to infinity, or from our negative infinity all the way to 0. So we're just not even going to consider this because we know it's going to 0. So let's just focus on our two integrals over here. So let's take a look at that. If we simplify this out, we get the integral from 0 to 1 of x squared dx plus the integral from 1 to 2 of, if we expand this out, we get 2x minus x squared dx. So these are decently simple integrals to follow. We can just use the the power rule over here. So the integral here is going to be 1 over 3 x to the 3, and we're taking that from 0 to 1. And then over here we will have x squared minus 1 over 3 x to the 3, and all this from 1 to 2. And now let's go ahead and fill in our bounds. So we have 1 over 3 x, or x will be 1. 1 to the power of 3 minus 0. So we have our first one, plus the second one here, we will have 2 squared minus 1 over 3, and then 2 cubed, so that's 8 over 3. And then all of that minus when we sub in 1. So we have 1 squared minus 1 over 3. Okay, so that is our integral. So let's go ahead and simplify this. So we have 1 over 3 plus, what do we have here? 4 minus 8 over 3, and then minus 1 plus 1 over 3. So let's simplify this some more. So we have 1 over 3 plus 1 over 3 plus 8 over 3. So it's nice we have the same denominator here. So we have 1 minus 8, which is negative 7, plus 1 is negative 6. So we've got negative 6 over 3. And then we have our plus 4 minus 1, negative 2 plus 3. And that equals to 1. So that means that the expected value is 1. So if we imagine this problem to be the amount of time a person has to wait for an elevator, that would mean that the person would have to wait 1 minute for the elevator on average. So let's take a quick look at what a graph of this problem would look like. So if we were to go and actually plot our probability density function, our PDF, so where our y-axis is our PDF and our x-axis is our random variable x. So we have this piecewise continuous function that goes up like this and then down like that. So at its peak over here, the function has a value of 1, and we know that it goes from values of x from 0 to 2, and it is 0 otherwise. So we can see here that it reaches this peak when x is equal to 1, and we can see that the peak has a value of 1. So this arrow over here that I'm drawing, this represents the center of mass. So that's a new word we learned today, center of mass. So the center of mass is another word we can use for the expected value of our continuous random variable x. So it's neat how we can do this algebraically, and then we can also go back and just look at our PDF, this is our PDF, right away, and determine what is kind of that center point, that average. And since this graph is perfectly symmetrical, we can see that our center of mass, our average, or expected value occurs exactly at the center. So that's like cool that you can look at it both ways, algebraically and graphically. And so today we covered lots of different things. We looked at expected values of discrete and continuous random variables, as well as their variance and other manipulations. If you have any other questions, please drop them in the comments, and please like the video if you enjoyed it, and please subscribe for more. I look forward to seeing you next time.